vertical load on point C. Direction is not matter. It doesn't matter for us. I'm using down direction. Therefore, my assumption is displacement on down direction. But if you think that displacement in up direction, okay, you can use the up direction. If you make a mistake, you don't worry about this, because if you obtain a negative value, this means that you get your assumption is wrong. You will change your assumption, but it doesn't change your you don't need to resolve your question, just only change to displacement direction. Okay, so my assumption in down direction, then I put a unit force vertical. This is the virtual loading. By using this loading type, I can find two member forces. First of all, I want to start with the point B. I choose, and if I throw the free body diagram in here, F, A, B in here, also in here, F, B, C. So there's no force, therefore sigma Fx is equal to 0 from F. AB is equal to 0, sigma Fy equal to 0. You can see FBC is equal to 0. I want to pass to the point C. Okay, we have a virtual loading 1 in here. Also, we have a two members, FDC and FAC. Sigma Fy is equal to 0. We can see FAC is equal to square root 2, but negative. That means the compression. Also, F sigma F x equal to 0. You can see FDC is equal to F minus FAC times cosine 45 degree. This degree is 45. Okay, and I can see FDC is equal to positive 1. And I can put this value on our screen. Okay, and also in the table you can see 0, 0, 1 minus square root 2, 1. Okay, now I generate the table. I want to use the copy and paste the Excel file if I can be successful. Actually, where is my slideshow in here? You remember? Is it this? I can delete this part. Okay, wait, and I can copy and paste. I hope I can be successful. I haven't tried. Yes. Remember, unit loads and like this. Okay. So I want to go back to the slide and general formulation. You can see for truss structure or formation, small n, capital N divided by EA. I'm sorry, this formulation, not this one. Yeah, small n, capital N, L over EA. Therefore, in multiplication of this, and I want to take first of all EA and as a constant. Okay, and this is equal to small n times capital N times L, and I want to sum this one. Also in the question is where is the I want to go back, and area is 400, modulus of elasticity equal to 2000. Therefore I want to go back to my slide. Okay, you know, unfortunately I forgot to multiply by 1000 in here, and I want to convert to this force to Newton. That I want to put to 1000. And no, sorry, I made it. Yes, in here. and copy and paste in here. Okay. Now I am working with the Newton millimeter. I want to add the area. Area is the 400 and for all section. Also modulus of elasticity. I want to convert to the megapascal. Therefore, I have to write the 200,000 in here. Again, I write in here. Okay. So I'm very awareness and small n, capital N, L divided by in parentheses EA, like this. And okay, expand the graph. Yes, here we go. And divided by in parentheses E times A. Sorry, forgot the parentheses. Yes, now it's okay. Then this is sum is equal to delta is equal to sum of this, and we obtain 0.012. Let me check our formulation first. Delta is equal to 0. Summation of this, so delta displacement is 0.012 millimeter. Let me control our system. You can see. Oh, actually, I made a small mistake in here. I think that 400 millimeters square kilonewton. Length, sorry, I also forgot to change the length. Is also in here. Where is it? The length. Also, length is. I forgot to convert to the millimeter. Okay. This unit conversion is extremely important article questions. You can see. Okay, so displacement is in the millimeter is 12 millimeter. Okay, this is the end of the question. I am using the Excel to understand easily. Okay. Also, if you want, you don't need to look like a new table. Also, you can calculate separate these values and sum these values. Also, you will get same results. Okay. Also, shape is missing. That determine the displacement on point on the figure. Figure not available in here. Just let me few seconds to find the formulation, lecture notes, dynamic, and strength of material. Yeah, not this one. Strength of material. Come here, like this. Find the original shape in here. Where is it? Yeah, this one. In the question, we have no numerical value in here, but it doesn't matter for us. You can, and we have two types of loading in here. I want to open the camera. Okay. And delete the previous question. We have two types of loading. Okay, first loading type is a real loading. You can see we have this is the cantilever beam. We have a omega function in here. This is a real loading. Okay. Also, we have a beam and also we have the put of virtual loading. So in the question, determine the displacement on point P. Therefore, I put a vertical displacement on point P. Therefore, this equal to 1. This is also virtual loading. So in here we have a two type of the moment. Okay. First of all, I have to, for the moment diagram, moment formulation here, mx. You remember, I want to take a cross section. I already did in previous examples, but I want to pre-obtain how we can find the mx. I will take a cross section anywhere of the beam. Okay, in here we have a W section. We have a cross section m as omega x. We have an x over 2 in here. Okay, so mx is equal to minus omega x squared over 2. You can see. For virtual loading, again we have a point load in here, 1. Okay, in this x direction and moment in here, you can see. Sorry, not m. I'm gonna use a small m. And small mx is equal to, you can see, minus x. So I obtain two m values, and I want to apply these values in the formulation. So I want to go back to the formulation. Where is my formulation? You can see displacement is equal to small n capital M divided by EI. So I want to write the delta is equal to small m times capital M divided by EI, like this. Sorry, it's not this one, it's like this. Yes. dx from 0 to L. So I'm using two substitute formulations. You remember minus x for small m, capital X for omega x squared over 2 minus in here divided by EI dx. After multiplication, I can see omega EI I can put out of integration. In integration, you can see x cubed over 2. I will also move to 2 in here. Okay. After integration, you can see omega x to the power 4 divided by 8 EI from 0 to L. If I substitute in, if I substitute in here, I can obtain the delta is equal to omega L to the power 4 8 EI. Okay, this is the result of the question. Let me control. You can see displacement is omega L is 4 divided by EI. If to determine the slope of the beam onshore, EI is constant. Okay. Also, there's no numerical values is given. Again, we have a controller beam. Okay. We have two types of loading in here. First of all, I want to start with the real loading. Okay. Actually, I need to change to our axis, the direction of the axis. Okay. And first of all, I want to draw. Okay. This is point A. We have a P. This is the real loading case. Sorry, I forgot to maximize the system. Real loading case, okay. So this is a real loading case. Again, we have a beam in here. For beam, we can see point B in the middle of the beam. The question asked the slope. Therefore, I put a unit moment because slope is needed. Therefore, I put a unit moment in here. This is the virtual loading. Okay. First of all, I want to start with the virtual loading because in virtual, if I want the virtual diagram, you can see from. I want to also explain that this is the start origin of the axis. I want to take the x-axis. Okay. from level 2, level 2, there's region 1 and region 2. And for region 1, you know, mx is equal to 0. For region 2, you can see I want to take a cross section in here like this. And this is a x, okay. Also sorry, like this direction, okay. You can see this is 1, m is equal to exactly 1 for virtual loading. So from x from 0 to L over 2, m is equal to 0. From x changes from L over 2 x L, okay, m is equal to 1. Again, I take an origin from here and direction x direction like this, okay. In order to simplify our calculation, I am using this strategy. So I obtained m, and also you can see I want to also obtain the moment value. You can see I take a cross section anywhere of the beam, and you can see in here we have p, we have a moment in here, we have an x, you know, m is equal to minus p times x in here from 0xl. So you can see to small m we have the moment change in two separate parts. Therefore, you know, our function is not continuous. Therefore, I divide the integration. I have to divide integration from 0 to L over 2, small m 1, capital M divided by EI plus from L over 2 to L, small m2 times capital M divided by EI. You know, this term is equal to 0 because m1 is equal to 0. But the second term is m2 is 1. Therefore, I want to continue this formulation. You know, L over 2, sorry, I want to delete this part. Where is my eraser? I hope you can see. From L over 2 to L, m2 is equal to, you remember that the 1 times m is equal to, you remember the minus, I'm sorry, actually it's minus 1, it should be. I made a small mistake in here, sorry that. Minus p times x divided by ei dx. dx is forgotten in here. Then you can see, you know, p constant, minus 1 plus minus positive, just x squared over 2. Therefore, you know, p divided by ei integration x squared over 2 from L over 2 to L. By applying this formulation, we obtain, I want to delete this part, okay. Delta is equal to PEI, if you put the L square over 2 minus L square over 4, 8, and after that we find 3P L square over for like 8 EI. Where is the not delta V? This is theta P. This is a slope. Okay. This is our solution of the example 14.8. Okay. This is the virtual load. Also, the principle is extremely simple. I don't want to use this formulation. I don't want to complain your brain. Okay. If you look at my solution, you will easily understand. Okay. Okay, the last subchapter is the Castigliano theorem. Okay, Castigliano theorem, again, I want to, for linearist, I don't want to go in detail. Just I want to say that, you know, in order to obtain a Castigliano theory is simple. For example, if you want to measure any displacement or system, okay, you put a force in here, P, okay, and you calculate the strain energy by using that force, okay, and if you take a derivative with respect to that force, we can obtain the displacement. This is the theorem of the Castigliano, first theorem of the Castigliano theory. If you reverse, if you put a displacement, try to calculate the force displacement, and if you take energy with respect to displacement, strain energy, and if you take a derivative of the strain energy with respect to the displacement, we obtain the P. This is the Castigliano second theorem. This theorem is simple, okay. I think that this is actually is a good thing that solve example 14.6 using Castigliano theorem. Okay, how we can apply this? I don't want to go in detail, just I want to explain. Actually, in 14.8, I want to 6. Okay, in here, determine the vertical displacement on point C in truss shown in figure. So, you know, in here, you remember that we put a vertical load and from virtual loading, which is whose value is the 1. For Castigliano theorem, we put a force, P force in here, okay? And we don't need to have any two type of loading type, okay? We put a force in here, okay? We have both, okay? P force in here and 100 kilonewton in here, and we try to find all member force by using this loading system. I think it's a good thing that to drawing in my in this question. If I want to use the Castigliano theorem, I want to draw to our truss again. Okay. For Castigliano theorem, I'm sorry, this is not this is a curve like this. Okay. For Castigliano theorem, we don't need to separate two types of loading. We have one type of loading, but we have put an extra term where we find the displacement on point. Okay. First, we have. I want to put the load 100 in here. Okay. Additionally, the question the vertical displacement on point C. Therefore, I want to put a P in here. The point load is available. Is there any normal force point load is in here? Okay. You don't need to put a P in here, but there's no loading on point C. Therefore, I want to put a point load. Okay. This is my loading case. Okay. I compute the member forces by using this loading. Then after that, you can see, I don't want to recalculate, just I want to show, you know, some terms you can see the AB and BC is not depends on P, but AC and CD is depends on the P force, therefore no normal M force in here, okay. And after that, we take a derivative of these terms with respect to the point force. You know, 100 is not depend on the P, therefore derivation of this term with respect to P is equal to 0. Similarly, member BC is like the same, but this term is, you know, sorry, depend on the P. I think that I need to change this, not like this. And also this is equal to 1, okay. Then I put a normal force in here, N is equal to -4. By using this formulation, okay, we can get the displacement. Okay, this is a solution. This solution is a little bit long, therefore I don't want to. Okay, I'm sorry that also what is the formulation? Well, how is it changed? For truss, okay, When we take the derivative of the strain energy with respect to P, we have a n square of 2, and also n is depends on P, you know. N times 2n is disappear, you know, sorry, this 2 is available in here. When we take 2, you know, n square root 2 and divided by 2 disappear, therefore this formulation is like this, becomes like this. Okay, we obey this formulation. So in parentheses, I obtain 2 terms. How many terms in here? The normal n, derivative of n with respect to P, and ln EA. I put in this one and I divide it in and I obtain same value. And I want to do example 14.7 using Castiglione theorem. I want to solve my, you remember that I want to solve my hand calculation. I don't want to use the weather calculation here. Okay, so I want to open my camera. Okay, going back to the question. Is it 7 in here? Yes. So in the question, we have a system, truss system is a normal loading in here. Okay, omega. So they want to vertical displacement on point B. Therefore, I'm sorry, I put to P load in here, but we don't know the value of P. Okay. So I want to find the normal and moment diagram with respect to this term. I want to take a cross section in here, and like this moment, this is omega x, this is P in here. Okay, this is x divided by 2, this length is x, just, I'm sorry, capital M. Mx is equal to minus Px minus omega x squared divided by 2. So dm over dp is equal to, you can see, minus x in here. Because, you know, this depends on p, therefore derivation of this term is minus x, but this term is not depends on p, therefore second term is 0. So remember, when in Castiglione theorem, our formulation, where is it? And beam, we will use the formulation m times dm dx ei for finding displacement. I want to apply this one from 0 to L. Okay, where is the m? M is equal to minus p times x minus omega x squared over 2 multiplied by negative x divided by ei dx. You know, I put the p load, but in actual, p is equal to 0. You know, I put the p load in here, but in reality there is no p load in here. Therefore, I want to write the p is equal to 0. Okay, so some of you asked, Hocam, why we are using the p instead of why we are using to put a p even the value is equal to 0. Maybe I can say, you know, in order to take a derivative moment with respect to p, I need a p, therefore I put a p. In actual, is there any real load available on p? I don't need to put a p in here, but I am unlucky, there's no p in here. Okay, therefore I need to write the p in formulation. Okay, let's continue. Now when this term is equal to 0, its integration is similar to like this, minus omega x cubed over 2 ei dx. Also, we obtain same integration in example 14.7. If we continue, we will obtain same displacement. Where is it? Displacement omega L cubed over 8 ei. So this is the end of the question. Maybe if you're wondering that if you want to solve example 14.8 by using the Castiglione theorem, don't forget to put a moment on point B and take a strain energy of the system with respect to moment. Don't forget this. Okay, anyway, I made a little bit mistake. This is the 9. It should be 9 because it started from, it's finishing the 8, and this is the last example, example 13.10. Hopefully you understand my telling. You know, strength of material is very boring for you and tiring course, and so many mathematical formulations, theories available in this course. I'm trying to tell you in detail. Also, you know, I want to simplify as I can, as simplify it as I can. I hope you understand the questions and understand the theories. If you have any question, okay, please let me know. Also, see you on final exam. Take care. Bye bye.